Before I start off this video, I need to explain parametric equations. A parametric equation is simply an equation that has two different equations, one for the x-coordinate and one for the y-coordinate. One that you are probably familiar with is the unit circle, which has a parametric equation of cosine of t sine of t. With this introduction being over, I shall introduce the parametric equation that has dominated my days over the last month, t cosine of t, t sine of t. This formula is a small change on the unit circle, but this small change causes the circle to become this. The multiplier of t creates this amazing shape, but this shape is also an amazing imitator. If you are familiar with polar equations, you probably remember this general formula for a Lymason. R equals a plus b sine of theta, or r equals a plus b cosine of theta, which creates a Limacon. The parametric equation creates a shape very close to this, but it isn't this. The reason is that the parametric equation grows because of the multiplier of t. It does this if you increase the bounds of t. A Lymason repeats itself over and over again while this parametric doesn't. The bounds we will be focused on for this video are negative 3 pi over 2 to 3 pi over 2. There is, of course, space inside the lines of this Lymason imposter. Being the masochist I am, I decided it would be cool to create designs inside this space. First, I decided that having a point halfway in each of the lobes would create a cool design. This creates a triangle in the center of the Lymason. Next, what if you create two triangles kind of like arms, like you were splitting the middle triangle in half, with two vertices being at 0, 0, and either negative pi over 2, 0, or pi over 2, 0. By doing that, you'll get this design. But look at all of that empty space in the center. We can have like a rhombus in there or something. Doing that gives you this design. At this point, my nerd brain started churning. Rhombuses have area, along with triangles. Is there a way I could get the area of both the triangles to equal the area of the rhombus? Of course, a question can have infinitely many solutions if you do not put restrictions on yourself. As such, I came up with some very arbitrary restrictions. First, the vertices. I will only be covering one side of the Lymason because this will be reflected across the y-axis. The vertices of the right triangle are going to be at 0, 0, pi over 2, 0, and an unknown point that we will call x sub l and y sub l. The rhombus will have vertices at 0, 0, 0, negative 3 pi over 2, and an unknown point which we will call x sub r and y sub r. More rhombus shenanigans, as the short side of the rhombus must have a length of pi over 2, so that it matches the triangle short side length. For this problem, I'm looking for solutions that look generally like the original rhombus and triangle shapes, but that doesn't mean that there are more solutions that don't form this design. The half of the rhombus is the easiest area to figure out. We can easily use the formula that you all learned in school, 1/2 base times height, with our base being 3 pi over 2 and the height being x sub r. Now, you may have noticed something here. We don't know x sub r. Since the base of the triangle is constant, the only thing we need to change is x sub r. If we can define x sub r based on the t value of the parametric equation, then we will be in business. Do you remember the way to find the area of a triangle with just the side lengths? No? Well, here it is. Heron's formula, S being all the sides added up and divided by 2. First, we need to find the side lengths. The top side length is easy. It's pi over 2. The bottom side length is also easy. We have the equations for both the x and y values on our Lymason. Using the distance formula with our x and y formulas, we get the square root of t squared cosine squared plus t squared sine squared. We can factor out the t squared to get cosine squared and sine squared by itself, which becomes 1 because of this trig identity. This leaves us with the square root of t squared, which is just t. This means the distance from the origin to any point on this Lymason is just t. The final side length is what makes this formula gross, though. We have the x value distance, which is pi over 2 minus x sub l, and the y value is just y sub l. We square each, add them together, and take the square root to get the final side length. We shall refer to these as a, b, and c sides. Get our s value, and then we use Heron's formula to get the area of the arm triangle. We can now set the two area formulas equal to each other and isolate x sub r. Now that we have x sub r, we can finally get y sub r by using the Pythagorean Theorem. We know that the length from the origin to x sub r, y sub r is pi over 2, and we know x sub r, so we can just do the square root of pi over 2 squared minus x sub r squared. The problem is that a square root always returns a positive value. So in order to get y sub r into the bottom right quadrant, we need to apply a negative sign. Now, if we pick a random point in the bottom right part of the Limacon, we can calculate the x sub r, y sub r point needed to make the areas equal to each other. Alright, technically the previous problem also had infinitely many solutions. We can pick any point in the bottom right of the Limacon and find a point that creates a rhombus with the same area as the two arms of the triangle added together. But now, what if we add another constraint? The rhombus vertice must be on the bottom line of the triangle. This creates a singular solution. Only one t value can create two equally sized triangles because the rhombus vertice is now tied to the location of the bottom right triangle. There are two ways to solve this. One in terms of x, then going into terms of t, which is super complex, or staying in terms of t but using calculus. We shall be doing solution 2 because solution 1 would take way too long to explain. First, we need to find the area of the second triangle. We could again use Heron's formula, but then one of my math professor's peers suggested that we just create a parallelogram and then take half the area. Let it be known that there is probably always an easier way to do the things you are trying to do. The area for a parallelogram of an unknown height is AB sine of theta. We know the length of b, pi over 2, and using the math from before, we know the length of a is t. Our theta would then also be t because it is the angle we plug into our parametric equations. This equation, though, splits out negative numbers, so we need to apply a negative in order to get a positive area. But in the end, this won't really matter that much. The more confusing part is going to be the area of the bottom triangle. First, we need to add a level of abstraction so that we can manipulate our equations better. Let's set a equal to t cosine of t and b equal to t sine of t, the x and y values respectively. We know the equation of the bottom line of the top triangle. It would be the slope of the Limacon point going through the origin. As such, our equation would be b over ax. Now that we know this, we need to find a point on this line that has a length of pi over 2. This is where the calculus comes in. We can use the arc length formula to find this point. We can set up the integral equation equal to pi over 2 from 0 to x sub r with the square root of 1 plus ba squared. The reasoning is that our line equation is b over ax, and the derivative is just b over a. We can then solve this integral to get pi over 2 is equal to the square root of 1 plus ba squared times x sub r. 0 does nothing and is not important in this integral, while the front part is just a very complex constant. Now we can pull out our algebra skills to get this simplified. We can multiply the front part of the square root by a squared over a squared, so that we can combine both parts under the square root. Once they are combined, we can distribute the square root to get this. The bottom becomes a, and in order to solve the top, we need to get rid of this level of abstraction. We again get t squared cosine squared plus t squared sine squared, which we know is t. So the final equation we get is pi over 2 is equal to t over t cosine of t x sub r, which becomes pi times cosine of t over 2 is equal to x sub r. This spits out a negative x value though, and we want it to be on the right side of the y-axis, so we will apply a negative. Using the previous logic of using the height of x sub r and a base of 3 pi over 2, we get the equation of the bottom triangle is going to be 1/2 times negative pi cosine of t over 2 times 3 pi over 2, which becomes negative 3 pi squared cosine t over 8 as the final area equation. We can now take the equations of both the areas of the triangle and set them equal to each other. Simplifying gives us 3 pi over 2 is equal to t times tangent of t. The height of the Limacon comes into play again. I never expected to see you here. You do weird stuff, Limacon. You are truly unique. The equation is obviously not solvable by hand, but using the Desmos, we can get that t is about negative 4.00764. This means that if t is negative 4.00764, then the areas of the two triangles will be about the same, and the point x sub r will be on the bottom line of the top triangle. Using the previous math from the first problem, we will also verify this answer. We need to zoom in super close to see any difference. This is the final design that forms using a t value of negative 4.00764 to get the vertices. This math probably won't change anybody's life, nor will it be groundbreaking in any way, as this is an arbitrary problem with arbitrary restrictions. Either way, it is an interesting problem that I wanted to share. Thanks to my calculus professor for helping me with all the math in this video. He rocks.